Hello everyone, I'm Audrika Iqbal and I'm going to start sharing my screen now. My project is titled Deep Reinforcement Learning for Energy Efficient Adaptive Subsampling in Predictive Object Tracking. So the motivation behind this project was that typical image sensors consume around 50 to 70% of the total energy in modern mobile systems. So in order to implement tracking applications, it requires a lot of energy, and we can solve this problem by implementing predictive object tracking, which can improve energy efficiency of image sensors and it can also prolong battery life. And if we integrate our predictive tracking strategy with ROI capable cameras, then that can result in three benefits: image quantization, faster bandwidth, and improved energy efficiency. So this is the problem statement that we're trying to do. As you can see in frame 1, the image sensor gets a fully sampled image. And then what happens is the predictive algorithm predicts where the object is going to be located in the next image frame, and it generates a sensor mask or a predicted subsampling mask, and this gets sent to the image sensor. These are the main contributions of my work here. So first of all, um, uh, there's a YOLO plus LSTM network, which is being used for feature-based ROI tracking and spatial subsampling. And uh, a policy gradient method is being implemented in order to train the LSTM network such that it is able to generate state control trajectories based on its learned parameters. Also, our network can be integrated with ROI capable cameras in order to improve the sensor energy efficiency. On top of that, we also propose a loss function which is based on both target location and subsampling mask in order to form a strong supervisory signal so that the network is able to converge much faster. And finally, we demonstrate the efficiency of a network in the context of energy optimization by making a report on potential energy savings as well as computational efficiency. So this is our proposed training approach. So as you can see in frame 1, we send a frame to a YOLO network which extracts features from it, and with it we concatenate the ground truth location as well as subsampling information. And based on all of this, the LSTM makes a prediction for the next image frame. Then this LSTM's information is encoded in its hidden state, which gets sent to the LSTM at the next time step. And along with the previous time steps hidden state, it also receives that frame's feature features, but not the ground truth subsampling and location information any longer. So basically, in a batch, only the first frame is getting the ground truth information at the training stage. And finally, the LSTM gets trained based on an episodic policy framework. So, where the reward function is a function of the ground truth bounding box and the predicted bounding box plus the ground truth subsampling pattern and the predicted subsampling pattern. This is the our testing stage. So basically, it's more or less the same processing through the pipeline. The only difference is that here we no longer extract features from the fully sampled frames, because as we know at test time we are trying to optimize the sensor energy efficiency, which we can do if we manage to switch pixels off outside of the region of interest. So that's the reason why, for other than the key frame or the frame in which the fully sampled frame is available to the sensor, we just extract features from ROI or subsampled images, and that's the only difference. This is our table containing comprehensive results. So I will highlight the most important parts here. So as you can see for our method, if you look at the MAP column, which indicates the mean average precision, or basically it is a metric of how well our algorithm is tracking the object of interest, you can see that we outperform all of the baselines for two of out of the three data sets. So for the ILS VRC 2015, we get an MAP of 0.6865, and for the tracking net dataset, we get an MAP of 0.6782. And not only that, but if you look at the ratio of pixels switched off, you can see that we managed to get the highest energy savings. And these three columns basically indicate the power consumption by modeling a realistic power consumption framework for a typical mobile system design. And as you can see, it has three different sensors, and for all three sensors, we get the highest energy savings. And these baselines basically we implement. So this is one baseline, which is a YOLO network plus a Kalman filter, and this one is kernelized correlation filter plus Kalman filter. This one is distractor aware tracker plus Kalman filter. This one is efficient convolutional operators plus Kalman filter. And these baselines, these last two, are not predictive, but these are there just for a base level performance comparison. So one is hours without prediction, and the final one is just YOLO tracking without any kind of prediction. So basically, for both of these, the energy savings are zero, but the MAP, as you can see, for our method with prediction off is actually the highest of all of the methods. So basically, we strive to reach an optimal trade-off between accuracy and energy savings. So with the highest accuracy, the energy savings is zero. So that's why we opted for a strategy where we could get high energy savings with a reasonable MAP. Okay, so this is a visualization of an easy video to track. So if you look at all of the videos, you can clearly get an idea that our method manages to stick to the object of interest for most of the image frames. For this next one, this is of a medium difficulty level. So at the beginning, our method is unable to track the object of interest because it didn't really have a lot of motion for it to be able to capture that motion. So when the coupon finally arrives, when it finally detects motion in the coupon, that's when it's able to track it better than the other baselines. As you can see, the other baselines are unable to keep track of the coupon and actually take larger bounding boxes than necessary. So not only does it deteriorate the accuracy, the tracking accuracy, it also uh, is not able to get good energy savings. So this is a difficult case for our method. As you can see, our method makes conservative predictions. So it basically takes the first image ground truth information and tries to create a bounding box which fits to the object of interest, the size of the object of interest, but it is unable to keep track of the player, basketball player in the green uniform, because there are multiple objects in the scene. So this is one limitation. So the next step for this algorithm is going to be we have to make it work for multi-object tracking so that it's able to keep track of the objects of interest individually. These are some results. So the first plot shows how our network converges with time. As you can see at the beginning, the test accuracy was very poor because the y-axis indicates the error, which is 1 minus the mean average precision, and the x-axis indicates number of epochs. So as you can see towards the beginning, the error was very high, but with time, the network gained experience in the reinforcement learning framework, and it managed to converge to an error of as that went as low as 30%. And this is a plot where we show that our method is able to sustain its tracking performance even with prolonged number of prediction steps as opposed to the baselines, for which the accuracy goes down drastically as we increase the number of predictions per keyframe. Finally, I would like to conclude the work by saying that uh, we have used a tiny YOLO network for feature extraction, and we have trained an LSTM for location and subsampling prediction, and our method is shown to uh, perform reasonably well for tracking in the context of object tracking while saving sensor energy, image sensor energy. Reinforcement learning driven tracking has been developed for energy aware sensors, and we have shown that adaptive subsampling based strategy can be used to achieve energy efficiency. And we managed to achieve up to 70% accuracy on a dataset with 7 times the energy savings. And that concludes my presentation. Thank you.